The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
So the presentation, the work is done by Dr. Eric Monzon. He is currently working as a lecturer at California State University, Sacramento, and also as a consulting engineer at EM Tecton Engineering. He completed his PhD in civil engineering at University of Nevada, Reno, with research topic on the performance of carved highway bridges. His research interests are in bridge engineering, earthquake engineering, seismic isolation, and development of advanced and innovative structural systems to resist extreme loads. So since he could not make it, I am just going through the slides. Okay. So this was originally, like, I am the co-chair of this session was Ahmed Abdel-Mohti because he recently moved to a new university. So anyway, so the topic is performance of horizontally curved highway bridge with seismic isolation. So this is the outline, Federal Highway FWHA curved bridge studies at UNR. So then seismically isolated curved bridges, talking about bridge response, experimental works, and isolators instability, and finally conclusion. So at UNR, they conducted a shake table test on a almost large-scale curved bridge, where they also had, live load on top of it, trucks. Although they are not moving, but they had trucks on the top of the deck. And the total length was 362.5 feet for the prototype. And they reduced it to almost like half model. The model was 145 feet. Like the prototype had 105 feet, 3 spans. But the model had also 3 spans with 42, 61, 42 feet. And the center line radius was 80 feet for the model, and the width was 12 feet. The girder spacings were 4.5 feet. Column height was more than 7.5 feet, and column diameter was 2 feet. So this is the setup where they used shake tables to perform the test, and also had the abutment. So this is the picture. What Muhammad just presented in his last slide in the thank you note. So I thought like Muhammad is familiar with this, and I was requesting him whether he can present it. So the experiments that they performed, it was conventional bridge, 104-degree bearings, 24-inch diameter columns. It has sacrificial shear key elements at the abutments. And the conventional bridge with live load, it had 6 trucks, and the bridge was isolated with 12 lead rubber bearings, and the hybrid isolated bridge with 6 LRB isolators and ductile cross frames, and they also considered the abutment pounding, and also the columns, they were rocking columns. So this is the lead rubber bearing that you see, which was placed underneath the girder, and this is the abutment showing here with the isolator, and this is the lead rubber bearing, like one at the abutment that was used and one at the pier level. At the pier level that was used. So the shear modulus was 55 psi. The abutment had a lower bonded diameter, 7.5 inch, whereas this one for the pier was larger, and the layer thickness was for each 0.25 inch, total rubber thickness 2.75 inch, total height 7 inch, and the lead core for the abutment was 0.25 inch less than the pier LRB, and the stiffness for the pier LRB was higher, 1.24 kip per inch, and the characteristic strength QD was 2.03 kip, so which was also larger. And this one is showing the performance of column in seismically isolated bridge. so the resultant moment in the columns, and this is the resultant curvature. And so they also tried to model it, and they found that the model and the experimental results, and also from the sectional analysis, they are kind of following what they found it experimentally. And from the shake table test, also what they have observed is when you have isolated bridge, the response as you are increasing the earthquake load, they are kind of proportional to the displacement as you increase the earthquake load, whereas for conventional details, you have this kind of nonlinearity. And they also have observed from the shake table that the pier experiences much lower shear demand compared to conventional bridge when you are using isolation, LRB isolator. You see it's significantly low compared to conventional bridges, and this is for pier number 2 and this is for pier number 3. So in both cases you see that isolation has benefit in reducing the shear demand in your bridge. And also, since this is less, obviously your bridge with isolation will experience less amount of cracks, as you see very minor cracks in your pier 2 and pier 3, whereas conventional pier you had severe cracks all along the height. So this is with 3 times the design earthquake level. So again, the pier with seismic isolation experiences very minor cracks, not visible, whereas in the pier with conventional details, you have large cracks that you can obviously see, and you see that they at the base they didn't even experience any spalling, and here you have significant spalling of concrete at the base at the plastic hinge region. And when they perform the shake table, they also experience during the shake table the isolator experience very large shear deformation, as you can see. They are going completely out of plane. I guess we might have a video, I'm not sure. So, and they were actually experiencing more than 200% shear strain. So you see at 3 times the design earthquake due to excessive displacements, instability occurred at one of the isolators at the abutment. However, the global instability did not occur because the isolators and other supports remained stable. This in addition to inertial loading in the bridge, the unstable isolators were able to return to original position at the end of the excitation, and they did not observe any residual displacement. So this is the video. Let me run the video. Okay. So it looks very flexible, the LRB. So it is coming back to the original position. So again, this is 3 times the design level earthquake. Okay, so proceed. So this is another video. So slow motion showing how the deformation is taking place. So we can see some rolling, and even like with large shear strain, it is even touching that steel plate. So this is interesting. If you look into the histories of LRB, you know that you expect under very large shear strain some residual deformation. But from this test, they found that there was no residual deformation. So which obviously, I'm not sure, maybe there is something that is not regular LRB. So if it is regular LRB, you expect there will be some residual deformation, but it did not have. So now it's coming to the very stable position. Okay. So the concluding remarks, essentially elastic behavior columns can be achieved in a seismically isolated bridge even at earthquake levels equal to 3 times the design. In a continuous curve bridge with multiple spans, instability of isolators at 1 or 2 supports does not lead to bridge collapse. And lead rubber isolators are highly resilient seismic protective systems. Extreme deformation and instability in these isolators has minimal effect on their stiffness. Okay, so that's the conclusion, and thank you for your patience. Yes.
You had that much movement at the bearing point.
Yes.
Could you comment on the structural ramifications to the surrounding elements that might be affected by that movement? If that happened, if the hypothetical case so happened?
Yes.
Damage surrounding it, essentially.
Obviously, yeah, like I know you came late, like this is not my research, but I'm presenting on their behalf, so I was not present, but obviously when you have this much of large shaking around, you may experience, if you did not design other elements so that you can have this kind of deformation, obviously you'll have many kind of damages that you can experience, yes, for sure, yeah. Yes. If you have any question, you can definitely contact Professor Ian Buckle, who actually was the lead investigator at University of Nevada, Reno. Or if you have any other question, we can definitely discuss. Any question? Okay. Thank you.